Hello, my name is Sean Farkas, and I'm a developer on the Project xCloud team. I work primarily on the developer hooks that we're building so your Xbox games can be enhanced for game streaming. With Project xCloud and Xbox console streaming, your Xbox games can now be played in ways that were never before possible. Today, I'd like to spend some time talking about the tools and APIs we make available if you'd like to enhance your game when it's being streamed from Xbox. First, we'll talk about getting your dev kit set up to build a cloud-aware game. We'll talk quite a bit about the Touch Adaptation Kit, which allows you to build touch controls for your game without modifying its input stack. And we'll spend a bunch of time discussing the cloud-aware APIs, which enable your game to detect that they're being streamed and enhance in any number of ways that they would like to do. I like to think about enhancing your game for streaming in 3 different phases. First is a console native game. And console native games are just standard Xbox games that run in our data centers or from console streaming. And this works because the data centers are effectively hosting Xboxes in racks. As far as the game knows, it's running on any other Xbox. In the Xbox console streaming case, it actually is running on an Xbox in someone's living room. The Touch Adaptation Kit allows you to build a set of touch controls without modifying your game's code. You describe declaratively the way you want those controls to look. The client application will render them and send X input style inputs back to your game. Once you become cloud aware, your game can detect that it's streaming and do all sorts of things. It might want to adjust its font size and UI layouts to match the device it's streaming to, for instance. And this will work both with Project xCloud and with Xbox console streaming. Before you get started, we'll need to set up your development environment. Our goal in building this development environment was to be as minimally impactful as possible. We don't want to impact the tools and scripts that you already have when you build your game. To that end, what we've simply done is enabled a new mode on your dev kit, which enables it to act as a streaming server. Of course, you'll need something to stream to, and that's where the content test application, or what I'll call the CTA throughout this talk, comes into play. The CTA is effectively just a version of the public game streaming app, but it has one special mode called Direct Connect that allows you to connect it straight to your dev kit. The goal here is that you don't have to change your workflow. You have your existing tools and scripts. You have Visual Studio and Pix, and all of that's going to continue to work. The only thing that we wanted to change was enable you to make modifications to your game to detect that it's streaming and just check how that works right at your desk in your normal course of work. So let's take a look at the way you would get your dev kit set up. You can see here we've got a new streaming tab on Dev Home on a dev kit on the left, and a Direct Connect page on the CTA on the right. The first thing you need to do is check that the streaming protocol version from the CTA matches the version that the dev kit is set up for. And typically this is already going to be the case. However, when we roll out new versions of the protocol, what we'll typically do is leave the older versions available on the dev kit so that you're not required to upgrade both your Xbox and your app in complete lockstep. The next step is to enter your Xbox's IP address in the Direct Connect screen of the CTA and connect. Now, one implied requirement here is that the dev kit and the CTA need to be on the same network so they can communicate with one another. Depending upon your studio's network setup, you might need to work with your IT department to get a network which can house both the Android device running the CTA and the dev kit hosting your game. Now with that out of the way, let's get started making some modifications to our game. At its core, the Touch Adaptation Kit is just a technology that allows your users to provide Xbox controller input to your game without using a physical Xbox controller. Instead, we'll render on-screen controls that the player interacts with using touch, and those are converted to X input style controls for your game. That is, the Touch Adaptation Kit allows you to build customized touch controls for your game without modifying your game's input or render stack. Now, of course, an Xbox controller has 18 distinct inputs on it, including 4 analog inputs, and that's an awful lot to place on the screen at once. Many games also require multiple buttons to be pressed at the same time, which may not be as easy to do using on-screen controls that are mapped to individual Xbox controller buttons. Now we could do it, and this layout does represent every possible button that a player could interact with, but it's obviously not an ideal way to play your game. And this helps to highlight why we've made touch controls opt-in. We don't want to allow players to play your game in a way that's not the most fun. So instead, we're going to have game studios figure out the best way to play their games with touch, and until they do that, we're going to have the game be Bluetooth only. Before we move on, however, we can see here that a fundamental way the touch adaptation kit's designed is around player ergonomics and customization. The places where a player's thumbs are most likely to be are highlighted by the gray bands here, and that's where we place the touch controls. That's sort of a fundamental feature of how the touch adaptation kit is designed. When you're building a touch adapted layout, what you're doing is you're basically selecting a control, mapping it to some actions, and placing that into a socket described in JSON. Sockets can go in a variety of places. We've got primary wheels for left and right thumbs. We've got sockets at the top and bottom of the screen for lesser used actions. And what this really does is it allows a player to build up a muscle memory. They can figure out where are the controls going to be for each individual touch-enabled game that they play. It also allows them to customize how they want the controls to be on their devices so that they can play in a way that's most comfortable for them. Now, when you pick where your controls are going to go, primary actions are really going to be mapped to the two thumb wheels because that's where the player's thumbs are going to be. That's going to be the most natural place for them to interact with your game. Lesser used actions go on the top and the bottom. Typically putting the menu and view button on the top makes a lot of sense. Putting secondary actions like checking your inventory, something that you don't necessarily have to do in the heat of action on the bottom, also makes sense. You'll also see that we reserved 3 sockets for system use. The Nexus button is always in the center of the screen. The upper left of the screen has a button to interact with the game streaming app, and we've reserved the upper right button for future use. By placing controls into wheels, it allows the players to customize exactly how they want the controls to be on their device in a place that's most comfortable for them on each different play that they play. They can adjust the size, the rotation, even the relative position of the controls. You can see here that this layout has being customized by the player, but there's 2 layouts in play here. And once they figure out exactly where they want to put those controls, the app's going to remember where those wheels are. And then when they switch layouts, it's going to be exactly where they expect them to be for all future games. And this is really one of the main benefits of grouping controls into abstractions like left and right wheels. It lets the player put the controls where they want them to be and not have to have the app worry about or the game worry about exactly where the most comfortable spot for a control to be is for a player. The Touch Adaptation Kit supports a variety of controls, each of which can be customized for your game. The most basic control is the button. And the button can be assigned to 1 or more Xbox buttons, from the face buttons, ABXY, to even an analog button like a trigger. If you map a button to an analog, what will happen is we'll report back that that trigger is fully pulled down, for example. If you map it to a face button, we have a little special rendering where we'll put a subscript that gives the name of that face button and the color of that button on as an addition to the icon. And that really helps us bridge a gap. For example, imagine your game is displaying some on-screen help. Press A to jump. Well, the player doesn't have an A on their touch controls, but they do have this subscript that lets them know this is the button that's being talked about. You can also map a button to chords of buttons. So you can have a single on-screen control. That's the combination of, for example, right button plus X, so that players don't have to use 2 thumbs to enter complicated chords into your game. Next up is the arcade control. And this is mapped out like 4 to 6 buttons would be on an arcade cabinet. The advantage here is it lets you press 2 or 3 buttons at the same time fairly easily. If you press between any 2 buttons, both of them get selected at the same time. If you press the little dot at the top or bottom, it selects 3 at the same time. And you can imagine this is really useful when you build the layout for a fighting game. We support 2 different types of joystick controls, which are typically used to map to the thumbsticks. At the top is just a standard joystick. And at the bottom is what we call a touchpad, which feels to a player a little bit more like a mouse trackpad might. And that makes sense because on a touch screen, it's a little more akin to doing mouse type input than it is to doing joystick type input. Joysticks can also be mapped to a single axis. So at the top here, we have a driving control, which is mapped to being the horizontal axis only. Typically, if you're using a thumbstick to drive, you're not wanting to go up and down. And by mapping this to a single axis, we've made it so that the player is more likely to be able to be giving the input to your game that they want to give. At the bottom, we have a throttle control. And this typically maps really well to an analog input. You can map it to, say, a trigger, and if you slide it up to 70% up and let go, it'll report to your game that, for instance, the trigger is pulled in and locked in at that spot. We also support a D-pad for games that really just want to have a whole D-pad on screen. Each of these buttons may have different icons associated with them, and this really helps bridge the gap between players that are used to playing on mobile devices and may not be as familiar with the A, B, X, Y of an Xbox controller. You can see here a subset of the icons that are available. And it lets you do things like have a jumping icon for the A button, have a steering wheel icon for the thumbstick. That really helps players understand what the on-screen controls might do. Let's take a look at some examples of what you could build with this next. A 2D platformer typically plays well with a D-pad, so we've mapped that to the left wheel. On the right wheel, we've placed run, jump, and attack buttons mapped to the face, as well as buttons for a trigger pull. An arcade fighter is also going to use the D-pad, but here we want to use the arcade buttons control for the punches and kicks that are typically used in a fighting game. For a driving layout, we can use a steering joystick on the left, gas and brake pedals on the right. In an adventure game, we might want to put some auxiliary controls around the primary wheels, using a touchpad to handle looking around, while we have a joystick on the left to control movement. In the first-person shooter, however, we can use those same joystick and touchpads, but we might want to move all the auxiliary actions to the right hand, since we're probably going to be on our movement stick fairly consistently during gameplay. Similarly, an action game might have a set of controls to use when you're locked on a target that puts movement on the left stick and a series of attack face buttons on the right, forgoing any sort of analog input on that side. Let's put this all together and build a simple layout for the first-person shooter game for the Unreal Engine demo. On the left thumb wheel, we're going to want a joystick to control moving around, and we'll configure that to map to the left thumbstick. If a player is moving their thumbs to the far outside of the joystick control, we'll want to configure it to additionally send the thumbstick click so the player starts running. Shooter games controls, like a lot of first-person shooters, transition a player to running when it sees that thumbstick click. By enabling the click to happen by a player simply moving their finger outside of the radius of the control, what we've done is we've enabled them to not move their hand off the control joystick, to have to press another button. Instead, it sort of naturally happens. As they move their hand a little bit further and further away from the center of the control, the game gets a report that the thumbstick is moving further and further. That's going to enhance how the player moves until it goes so far outside the control that we report to the game the player should be running. And that's sort of a really natural touch paradigm for players. In the upper left corner, we're going to add an icon mapped to the Y button to allow a player to switch their weapons. And with that in place, the left wheel will look like this. On the right wheel, we're going to want a touchpad to use for looking around. We're going to configure it with the dead zone that the game uses so that movement on the touchpad translates directly into movement on the game. We're also going to increase sensitivity slightly so we don't have to move our fingers very far to look around in the game. Around that touch wheel, we'll add some basic buttons to fire our reload, jump, and aim down our sights. And since we'll frequently want to aim down our sight for a period of time, we're going to make that button a toggle button, so the player only has to tap it in order to start aiming and tap it again to stop. They won't have to keep pressing the touch point on their screen while they're targeting at their enemy. And with that, we've now got both thumb wheels configured. All that's left now is to put the menu and view buttons at the top of the screen, and we should have the start of a touch-adapted layout to play shooter game with. This was really basic, and you'll want to do some play testing to make sure you're building a fun set of touch controls for your game. But with just a few minutes of work, and without modifying any of the game's code, we were able to build a really simple touch layout to play shooter game with. The touch adaptation kit allowed us to let our game receive touch inputs without any modification. However, we can do many more interesting things to our game once we crack open its code and make use of the cloud-aware APIs. So let's talk about those next. These APIs are designed so that you can enhance your gameplay when your game is being streamed, either from Project xCloud or with Xbox console streaming. Some of the modifications you might want to make include detecting that you're streaming to a phone and adjusting your font sizes and UI layout to work better on a smaller screen. When a player disconnects from your game, you might want to trigger a save automatically. For example, if I'm commuting somewhere, when I get where I'm going, if I'm not at a save point, I'm unlikely to be able to continue to play, and it's frustrating if I lose all of my progress. If your game has multiple touch-adapted layouts, maybe one for shooting and one for driving, it can ask the streaming client to toggle between them. You could even build some native touch interfaces to respond to mobile gestures more naturally. You might consider having two sets of settings, one for when I'm playing on my TV and one for when I'm streaming. This can allow me to change things like my auto-aim sensitivity or turn on steering assist when I'm playing on a phone, but play with my preferred difficulty settings when I'm playing at home. You might also want to consider saving different gamma settings. My TV at home is unlikely to have the same display properties as my phone. There's basically four main feature areas that are available in the API set today. The first one is touch controls, which allow you to both build touch-adapted layouts and also add native touch to your game. Streaming client management allows you to know when someone has disconnected from your game. And the streaming client properties allow you to find out more information about that device. Now, the latency measurement APIs let you measure how far your client device is away from your game. Since our Project xCloud servers are hosted in the Azure data centers, which has a global footprint, we're able to take advantage of that to place your game as physically close to your players as possible. However, the speed of light being what it is means that the time between when your player presses a button, when your game sees it, the time between when you render a frame and when your player sees it is going to be slightly longer than if it's on a living room Xbox. Typically, games work really well, but if you want to apply some algorithms that you know from your multiplayer work, the latency measurement APIs will let you do just that. Typically, when a game has different touch-adapted layouts, there's going to be a whole set of them that need to be applied throughout the game. If we think of a game like Halo, for example, the layouts that I'm using when I'm running around as Master Chief are likely going to be different than the layouts that I use when I'm in the Warthog. There might be a whole different layout when I'm in the back of the Warthog using the cannon. Well, how do I make this work? The first thing I need to do is build all of the layouts that are necessary for my game to work. I would build layouts for the first-person mode, for the driving mode, and any other auxiliary modes. I'll bundle those up into a touch adaptation bundle and upload them to the Project xCloud servers. Next, there's a set of APIs that are used at runtime to select between the different layouts. So this way, the client device knows exactly what layout matches the state of your game at any given point in time. Earlier, I gave an example about switching between the layouts if you're going between driving and action portions of your game. However, it's also possible you might want to switch layouts for more subtle state changes. Let's go back to shooter game. Now here, we have a touch-adapted layout that has both a reload and a shoot button because the player has extra ammo clips and their current clip is not full. But if the player runs out of all their extra clips, they can no longer reload. Now we could keep the reload button on the screen and allow the game logic to reject the request to reload the weapon. Or we can provide a visual hint to the player by switching to a similar layout which simply removes the reload button altogether. Similarly, when the player runs out of ammunition, we might just want to remove the fire button to provide another visual hint that they need to go find more ammunition if they want to continue playing the game. Now, when they pick up another clip, we'll probably choose a layout which supports shooting again, putting those fire buttons back on the screen. If we've built a touch-enabled menu system, we might want to dismiss the on-screen controls entirely, allowing the player to interact with the menu more naturally. To build this, it's actually fairly straightforward. We've hooked a few key points in the game logic. Things like I've gotten more ammo, I've run out of ammo, I've reloaded my weapon, or I've picked up a new weapon. And at those points, we send a message to the client app that lets it know the touch control layout, which most reflects our current state. Now, You want to strike a balance here. While it's okay to send a message to the client that reflects the same touch controls that they currently have, that's effectively a no-op, we really don't want to send an update every frame because that is sending a network message across to the client. Instead, the balance that we've decided to go with here is every time a state change occurs, we'll send a message to the client. And what we can observe here is that we're simply informing the client device as to the best set of controls that matches our current state right now. The client device does the rest for us. So imagine the case that the player is using a Bluetooth controller instead of touch controls for the game. In that case, we don't want to be popping touch controls on and off the screen because it's going to be very distracting. Instead, the client app notices the player's not using touch controls, or maybe on a device that doesn't even support touch. And in that case, they're not going to display them in response to the message. Instead, they'll say, okay, the player's not using touch controls right now. I'll make a note as to which are the controls that make the most sense to put up if they decide to switch to them in the future, but for now I won't display those. This way your game doesn't have to keep track of the state of the input on the client device. Instead, you just inform us if the player is using touch, this is the best set of touch controls for them to use right now. With those changes in place, you can see how we can provide context-sensitive controls to the player, providing them with hints as to what actions are available to them in the game by adding and removing controls that match the current game state. Now, we've been talking quite a bit about using the touch adaptation kit to create a set of touch controls for your game. And this works great for the most part of your game, which really just wants to see controller inputs. Now, for example, a racing game could use the touch adaptation kit to build an interface that has a steering wheel and gas pedal sliders for the majority of its gameplay. However, our user research tells us time and again, there are some things that happen during a game that players just really want to interact with natural touch motions. When a menu pops up on the screen, players want to tap it to interact. When a map comes on the screen, players want to use natural mobile phone gestures. They want to pinch to zoom and swipe to scroll around. Our SDK allows you to intercept these natural mobile phone inputs and provide mobile-first UIs or touch-first UIs for your game. So for instance, you can intercept that the player has tapped the screen and use that to build a touchable menu. You can get multiple touch points and use that to build a map that's interactable with swipe. So let's take a look at how we might do this with the Unreal Engine shooter game demo. Now, on the ERA and the XDK, the inputs to touch look exactly like the inputs for mouse. So we'll start by hooking the on-pointer press, on-pointer move, and on-pointer release events. And inside of those, we'll make a note to see, did I just get a touch? And if so, we'll make track of where that touch happened. Now, when we're processing the input queue, we can notice we have a touch event. And if we do, we'll just move the cursor to where the player touched the screen and hand off to the existing mouse handling code in the game. And in fact, with no changes to the game code, we have a menu system that responds to touch events from the player. And because we had no changes to the game code in order to make this work, we had a little bit of free time to make a few other options. So for instance, we were able to enhance the size of the menu to make it look bigger on the mobile device. We were able to add buttons to interact with the different menu options to change Booleans and to increase and decrease numeric values. We'll see more about how to do this in a few minutes. The most fundamental thing you're going to want to do when you're playing with the CloudAware SDK is detect that someone is connected to your stream and they're now streaming your game. And that's where the streaming client management APIs come into play. The most fundamental of these is xGame streaming is streaming, which returns true if anyone is currently streaming your game. But let's think about the console streaming scenario. With Xbox console streaming, I might fire up a game on my couch at home, play it for a little while and realize I'm late to dinner. So now I'm going to grab my phone, hop in the back of a rideshare, and connect back to my Xbox to continue playing on my way out. Well, in that case, my game is transitioned from not streaming to streaming. Now, similarly, when I get home from dinner, I'm probably going to want to keep playing in my living room. And in that case, I might disconnect my phone, and the game is transitioned from not streaming to streaming, or from streaming to not streaming. So that is to say that X game streaming is not a constant. It's a point in time statement. X game streaming register connection state change can be used to get real-time notifications for when these connect and disconnect events happen, so that your game can internally monitor its state and know someone has just started streaming and someone has just stopped streaming. So let's talk through the typical flow of how a game might monitor for these devices to connect and disconnect. The first step is just register for notifications when a device has connected to and disconnected from your game. Here, we'll shuttle those off to game implementation functions that handle the connect and disconnect logic. When a device connects, we'll want to keep track of it. In this case, we allocate a game-specific data structure to track the streaming client, stashed into a map indexed by its ID. So in this game, that means X game streaming is equivalent to checking to see if there's any data in this map. In either case, we know that someone is streaming. The ID is an interesting thing to talk about, because what happens is we will make sure that that ID is identical for the identical client playing your game. So if I'm playing on my phone and I play your game once, it's going to have some ID. I disconnect and I connect tomorrow, I'm going to have the same ID. But if I connect from a different phone, I will have a different ID. And this allows you to save per device settings. So if I have two different phones with two different gamma settings, you could potentially have two different sets for that and know which one I've connected with. The next thing we're going to do is register for notification when the properties of the client have changed. Here we'll understand what's the size of the device that just connected to me. And finally, we'll update the device that just connected with what the current touch control layout should be. Now, if a race is about to start and I connect in, I'd like for the game to tell me to put up the touch controls for driving, for instance. Now, when a client device disconnects, what we're going to want to do is take some action to clean up our state that's associated with that device. We're also going to get a controller disconnect associated with that client. And that works really great for console native games that aren't connected to this console state or client state management system. However, if you want to do something extra, like maybe trigger a save game, this is an excellent place to do that. On Project xCloud, the game is going to stay alive for a few minutes after the disconnect happened, so that a player who hits a temporary disconnect state, maybe they've driven through a tunnel, is going to be able to recover their session. So there's plenty of time for you to do things like trigger saves. You should also be aware that you might receive more disconnects than you might initially think. For instance, if I receive a text or I answer a phone call, that's going to trigger a disconnect from the game and then a reconnect when I open the app back up. There isn't anything special you need to do about this. You should just be aware that you might see more disconnects than you would initially think when you're walking through your game logic. After a streaming device connects to the stream, you're probably going to want to find out some more information about it. And that's where the Client Properties APIs come into play. In the API set that's currently shipping, there are two properties for you to query. You can get the physical size of the screen that's streaming your device, and that allows you to do things like change your UI layout to better match the device size. You can also find out if the device supports touch at all, and that's useful if you've done, for instance, a native touch-enabled UI on your side. If the device is not able to ever send you a touch event, you might not want to put up that UI at all. I do want to talk for a minute about the physical dimensions that are reported by XGame Streaming GetStream Physical Dimensions. These dimensions are the width and the height of the video frame of your game in millimeters. That is, they're the same aspect ratio as your game is rendering, not the aspect ratio of the device you're rendering on. So imagine a phone, for instance, with screen dimensions that are 150 millimeters by 65 millimeters. On that device, your game might be rendered pillar boxed. Maybe it's 110 millimeters by 62 millimeters. And those are the values that are returned by the API. You'll get the 110 by 62 size of your game's image, not the 150 by 65 size of the screen. Now we can make an observation about DPI using this. Since your game's rendering to a 1920 by 1080 back buffer on the Xbox, we can calculate a virtual DPI by dividing that resolution by the physical size of our stream. In this case, it'd be on the order of 440, rather than the DPI of the screen the game is rendering on. Let's go back to that shooter game demo again and put in some simple code that will detect that we're running on a small screen and adjust the font sizes that the game is using to compensate. Now here's a basic function we call whenever we get a notification that the screen size has changed. Here, we just do something really simple. We say screens that are less than 6 inches are small, between 6 and 12 are medium, maybe that's a tablet, and larger than 12 is a large screen. Maybe we're on a, attached to a monitor. With that in place, you can see how we scaled the text to be more readable on a mobile screen when someone's streaming our game. The original text size is on the left, the rescaled version is on the right. This additionally has the side effect for making the hitboxes for touch a little bit easier to use when you're using the menu as well. Now, of course, your designers might want to do all sorts of things in response to knowing the size of the screen they're on. This is just a really basic example. Another thing you can do with the Cloud-aware APIs is detect which Azure data center that you're located in. And this will let you do things like co-locate your game servers inside the same data center. Maybe matchmake between players that are located together so that they get nearly zero ping between them. One interesting thing to note is that we noticed some bugs when we were bringing up Project xCloud. Some games that were measuring the distance between themselves and their servers were seeing that they were getting a 0 millisecond ping and not reacting to that well, not thinking that 0 milliseconds was possible. And there's different ways you can handle this. You could just realize that 0 milliseconds is a possible ping between your Xbox game and the servers that you're talking to. Maybe you want to do the math in microseconds. Or maybe just the front-end code that's doing that ping knows that the rest of the code's not going to handle 0 very well and rounds it up to 1 when it detects it. Now, incidentally, this API is the one which is affected by the data center region name configuration setting we saw in the streaming tab of DevHome earlier. By default, XGame Streaming get server location name is going to return that your dev kit is not a server. It's going to return a null string. But if you want to test some code you've written that tries to co-locate servers, that tries to do something interesting with the Azure data center, you can put a string here and we'll report that value verbatim back to your game. And that's literally the only thing that this text box does here. We're not going to do other things like try to set up latency between yourself to match what you would be in that data center. It's just changing the location name. Next up, let's talk about our latency mitigation and measurement APIs. One thing you might notice, based upon what we were just talking about, is that the latency between two Xboxes, or latency between an Xbox and a backend server, might be significantly lower than what you're used to, especially if they're both in the same data center. What this means is that if you already know algorithms that help mitigate latency between Xboxes and their servers, you have a chance to reuse those algorithms just in a different location in your game. For example, you might want to apply some of those mitigation algorithms between your game and the player, as opposed to between one person playing your game on one Xbox and a different person on the next Xbox. Let's take a look at some of those APIs next. Now, of course, to do that, you'll need to be able to measure the latency your game's observing. And that's where xGame Streaming getStream added latency comes into play. It's going to return to you the number of microseconds of latency that are observed between when a controller input is pressed and when it's provided to the Xbox running the game. It also measures the number of microseconds of latency observed between when the game renders a frame and when the player sees that frame. The third value it provides is a standard deviation. Now, the input and output latencies are provided as an average over the last several seconds. The standard deviation lets you know the jitter that's inside of that average. So if you see a high standard deviation, maybe it's 8 milliseconds or more, that means that the network connection between your player and your game is pretty variable. The data points that went into calculating that average are kind of more widely spread apart. If you see a lower jitter between them, it might mean that those data points are more tightly packed together and the average that you get is a little more actionable. So if you call this API and you do see a high jitter value, you might want to go ahead and wait a few seconds and call it again to get a more reliable view of what the player is seeing. Now let's talk about exactly what's being returned to you by this API. When a player plays the game, they're going to press a button on their controller, which is going to go over a Bluetooth connection to their phone. The phone is going to pass it to the app, package it up, and send it over the internet to the console to be made available to your game. The Bluetooth controller latency is not included in the input latency, simply because there's really just not a great way for us to measure that. But the time between when the app receives the input and when it's available on the Xbox for your game to see, that's what's being measured as input latency. Once your game receives the input, it's going to run its game logic. It's eventually going to render a frame that responds to it. Maybe the player pressed jump, and eventually you render a frame that has the first jump animation frame in it. And that time between when your game receives the input and when it renders the output of it is not included in either input or output latency, because remember, we're measuring stream added latency. The time it takes your game to run is going to be the same whether you're streaming or not. Well, once you've rendered the frame, it's going to go through our video encode, get packaged up to sent back over the internet, and decoded on the client device, and then played on their screen. And the time between encoding, sending it, and decoding it is what's returned as the output latency. We don't measure the time that it takes to go onto the screen simply because, again, there's not a great way for us to measure that on every client device. Now, that diagram I showed you was obviously a lot more fine-grained than just input and output latency. So in the future, we're adding a new API that allows you to get more detailed statistics about the frame. And this really gives you a choice. If you want to work on the higher level, more bundled input and output latency level, you have the option to do that. If, however, you want to work and figure out exactly what the encode duration was, exactly what the decode duration was, you may do that as well. And in fact, you might want to mix and match. Some of your game logic might want to work on the just input latency average and output latency average numbers, while you might have some diagnostic code that wants to see the real details. This API is not available right now, but it's coming in the future, and it'll let you choose how you want to implement your game logic. Of course, if you've written any code like this, you're going to need to test it. And to do that, we've augmented the XB Stress tool with game streaming profiles. We've got a profile in there that sets up the latency that we've seen for minimum requirement to play on Project xCloud, the 25th percentile that we've observed inside our preview, and the average that we've seen inside our preview. And we've kind of kept things abstract this way so that we can keep the numbers up to date as our preview continues, and we can keep things so that you'll really be able to test to see what the real world Project xCloud environment looks like. Before we finish, I want to talk about another API that's coming in the future. This API lets you pass tokens between the server and the client back to the server to let you see and understand exactly what the client was seeing when they provided input. Let's imagine a situation where a player is playing your game with high latency. Maybe your game simulation is detecting that the player is aiming at an enemy, but that frame hasn't yet made it to the player's device. Well, when you render that frame, you can render it and tag it to say, yes, on this frame, the player is targeting the enemy. That tag gets sent along with the frame to the client device. Now, because of the latency of the connection, your game simulation has moved forward. The player is no longer aiming in the right spot. But as this is happening, the player thinks they are at the right spot, so they pull the trigger. When they pull that trigger, we send the state that you sent over to the device for the frame that's currently on the screen back to the game. And now you have a choice. You can process either what the current state is on your game simulation, or you can process what the state is in the frame that the player sees. And in this way, you can decide, should I treat this as a hit? The player thought they hit the enemy, or do I need to do something different? Now, obviously, your game state's not going to be something as simple as I'm targeting the enemy or I'm not, but this gives you an example of the type of thing you might be able to do with this token passing API, which is coming in a future SDK update. And that wraps up our quick tour of the APIs available today to make your game cloud aware. Hopefully that gave you some inspiration for experiences you could build in your game to enhance it when it's being streamed from Xbox. Now, we know our API set's not done, and if you did get an idea of an experience you'd love to build into your game, but you didn't see the tools or APIs there that you would need to do it, we would love to hear about it. We're definitely open to adding new sets of capabilities for you to build the experiences you want for your game. If you're interested in learning more about how the Project xCloud public preview has been going over the last year, you might want to check out another presentation given by my colleague Eric Cohen, where he goes through some of the things that we've learned during the first year of running the Project xCloud public preview. Otherwise, thank you for your time.